Welcome to Calc, Practical Calculus for the Busy Math Student. And in this video we're going to take a look at the numeric integration technique known as Simpson's method. Here we're trying to calculate the area under the curve square root of x squared minus 1 on the interval from 1 to 5. And it doesn't look too scary, but it's a pretty rough integral. It requires trig substitution if you're familiar with that technique. But we're not going to use that. We're going to estimate it using a numeric integration technique known as Simpson's method, which is named after British mathematician Thomas Simpson. He's an 18th century mathematician. However, there's some controversy here, as always in calculus. It's been predated to Johann Kepler about 100 years before in Germany, so we're back to the old English-German calc rivalry here. But most places refer to this as Simpson's method. So we'll go with that. Simpson's method estimates area under a curve using quadratic functions and what they call parabolic arcs. So unlike Riemann sums, which are rectangles, and trapezoid rules, and where we have geometric formulas, we have to derive a formula for area under a parabolic arc. And it's not geometric, it requires calculus, but it's pretty straightforward if you do the proof. But here's the result of it. It states that the area under a quadratic function q of x on the bounds from a to b, and I'm using capitals here just to keep the labels separate, but it's equal to the width of the interval over 6, b minus a over 6, times q of a, that's the height of the quadratic at the left end point, plus 4 times the height of the function at its midpoint of the interval, a plus b over 2, and 1 times the height of the quadratic on the second endpoint. So what happens is, when you're doing a Simpson's method, is that it combines two subintervals. So there's one big prerequisite to Simpson's method, and that's that n must be even. So you can do, for instance, trapezoid rule with 5 trapezoids, but you can't do a Simpson's method because it pairs these intervals up. But a lot of the other features of numeric integration are the same. For instance, delta x, the width of the subintervals, is b minus a over n. So in this example here, right, we're looking at delta x being equal to 5 minus 1 over 4. So delta x is 1. And that defines what we call the partition. Right? The partition is the set of cut points that define the endpoints of each subinterval. Where we basically start at a and we just move across the x-axis by delta x's until we reach b. So in this particular example then, our partition is going to be starting at 1, 2, 3, 4, and 5. So it takes 5 points to make 4 subintervals, and in our definition, when we refer to the partition points, we start with the first one being x sub 0, because of this fact that it takes n plus 1 points to define n subintervals. So the number 1 is x0, also known as the left endpoint a. Number 5 is x sub 4 in this case, right? Also the right endpoint b. So when we mark those out on our axes here, and we can draw what this Simpson's method is going to do, but it pairs up two subintervals. So it's really doing two area calculations from 1 to 3. And I'm going to put a little divider there so we can see the subintervals, and then from 3 to 5. So that's why you need an even number of subintervals. And what it does is it 3 points define a parabola. So it maps to the function in 3 places, and it defines the quadratic through those 3 points, which, because quadratics can have concavity, tends to match a lot of cases much better than, like, say, a Riemann sum does. So we're going to draw the parabola through these 3 points, and that's going to be the first 2 subintervals, and then we're going to take these 3 points, plot it to the curve, and define that quadratic. So if we look at each of the parabolic arcs and you start to see the formation of this formula, namely the weighting factors on the y-coordinates. For the first parabolic arc, the blue one, the weight factors are 1 for the left endpoint, which is 1. 4 for the midpoint, 2, and 1 for the right endpoint, 3. And then we have our second parabolic arc, which then uses 3 again. So that one's used twice. So now the weight factor on that one is actually now 2. And then the midpoint of that interval has a weight factor of 4, and then the right endpoint has a weight factor of 1. So because of that, because of the adjoining regions, what we see is every other interior partition point gets a weight factor of 2 because it's being used twice. It's an endpoint being used twice. And then the other alternate partition points have a weight factor of 4 because of the area of the quadratic formula we have here. The other interesting thing is that in Simpson's method we see a factor of delta x over 3 in front of all this. And the reason why is it's 2 subintervals to make one parabolic arc. So the width of each of those parabolic arc subintervals is actually 2 delta x, which is where the delta x over 3 comes from. So to help remember it, if you integrate a quadratic, x squared is x cubed over 3. So the 1/3 there is how we can keep that straight from, say, the trapezoid rule. So it's delta x over 3, and then we have this signature pattern of the coefficients on our partition points: 1, 4, 2, 4, 2, 4, 2, 4, and then 1. And by the fact that n must be even, the last interior partition point will always be a weight factor of 4. So that's Simpson's method. That's the survival part of it. And so if we use it for our example, and we look at our situation, we can state that the Simpson's estimate using 4 subintervals for our function is delta x over 3, so delta x here is 1, so 1/3. And then 1 f of x 0, so that's the left endpoint of 1, and then 4 f of x sub 1, so 4 f of 2, and then 2 f of 3, and 4 f of 4, and then on the right endpoint we have 1 f of 5. So the mechanics of Simpson's method, when we're actually calculating with it, look very similar to the trapezoid rule. And then we just go ahead and evaluate our function at those places. So we have 1/3. F of 1 in this case is 0. And then we have 4 f of 2, so 4 square roots of 3, plus 2 f of 3, so 2 square roots of 8, plus 4 f of 4, 4 square root of 15, and then 1 f of 5, which is the square root of 24. And then if you wish, you can simplify the radicals. So now we have 4 square roots of 3 plus 4 times the square root of 2 plus 4 square roots of 15 plus 2 times the square root of 6. And that's all multiplied by 1/3. So at this stage, if we're actually using this to estimate the area under the curve, we would get our calculator out and get a decimal estimate. So the quantity inside of the brackets there is approximately 32.976. And then we multiply that by 1/3 and we get our Simpson's method estimate of 10.992. So if you want to compare that with the numeric integration function on your calculator, which Simpson did not have, and neither did Kepler, but we do. So if you check that out on your calculator, you're going to find that it gives you a value of approximately 11.101. So we see here, even with just four subintervals, we have a very good estimate of the area under that curve in a case where doing the antiderivative is very, very difficult. And sometimes antiderivatives are impossible. So the numeric integration techniques exist for these types of cases. Even in the calculator age that we live in, it's important to understand that those built-in numeric integration features on your calculator are based on these ideas. And they can do them with many more subintervals and do all the arithmetic much, much faster. But your calculator can't do an antiderivative. It doesn't know how. So it's the theory behind numeric integration sometimes in the modern age that we pay attention to. But back in the 18th century when Simpson was around, this is a pretty good estimate for not too many calculations, really. So that's the third of our numeric integration techniques. There's Riemann sum, which uses rectangles, the trapezoid rule, which obviously uses trapezoids, and Simpson's method, which is based on area under a parabolic arc. If you'd like to learn more about Simpson's method or numeric integration techniques or calculus in general, you can find those on my textbooks available on Amazon for a nice price. Don't forget to subscribe to the P. Clark Calc channel. Till next time, I'm P. Clark.